Welcome back, everyone. This is now part B-1 of the 2017 Physics Regents. Part B-1 is, again, 15 multiple choice questions, but now these kind of require a little bit of math skills involved from what I've noticed. Not so much entirely math skills, but it's also mixed in with content, and yeah, it's a little trickier. Now, we're going to start with number 36. Let me expand this for a bit. Alright, so number 36 will always be this kind of a question. It's a metric estimation question. It's going to ask you to estimate the size of things, sometimes the mass of things. Most often it'll be the size in terms of like distance or height. And so number 36 is asking about the height of a typical kitchen table. And they give us the units in meters. So not only is it asking you to know the exponents and the powers of 10, but to also it's a good thing to commit to memory the size of a meter stick. Okay, so a typical kitchen table we would say is about 1 meter. And so looking at each of these choices, this is 1 centimeter, this is 1 meter, this is 10 meters, and this is 100 meters. And so our answer is choice 2. Number 37. A ball is thrown with a velocity of 35 meters per second. Alright, number 37, a ball is thrown with a velocity of 35 meters per second at an angle of 30 degrees above the horizontal. So here we have a vector, a velocity vector of 35 meters per second. And when they say 30 degrees above the horizontal is just a reference point. So it means this way. Our reference point is horizontal, not vertical from like a normal line, this way. So it's 30 degrees above this. Alright, we are looking for which quantity has a magnitude of 0 when the ball is at the highest point of its trajectory. Okay, so the ball is going to travel like this. At the highest point of its trajectory, right here, the horizontal component still exists, but the vertical component is 0. Okay, so the acceleration is still 9.81 meters per second squared going down. That's still there. Momentum, it still has momentum in the horizontal direction. Horizontal component stays constant, and it's the vertical component here that goes to 0 at the highest point because of gravity. All right, number 38. Here they give us a velocity versus time graph. The shaded area represents the toy car's displacement. Okay, so we can think of the area as the x-axis times the y-axis. Here it's space times height for a triangle. So your base here is the time, and the height here is the velocity. So you're multiplying these two things together to get the area. So V and T. This comes together from this formula. This all comes from this. When you multiply V and T together, you get D. So that's how we get displacement. If you're thinking acceleration, you must be mistaking for the slope. The slope of the line equals acceleration, because that's y over x. Okay, which is velocity over time in this case. Alright, number 39. This one's pretty straightforward. A spring stores 10 joules of elastic potential energy. When it is compressed, 0.2 meters. Okay. What is the spring constant? K is our unknown. And all you need is this equation. Okay, 1/2 K times 0.2 squared. K is equal to 500 newtons per meter. And that is choice 4 as your answer. Alright, number 40 and 41 are tied together. So let's start with number 40. And they go with this prompt. Here, a cannonball with a mass of 1 kilogram is fired from a 500 kilogram cannon. They're both initially at rest. The cannonball is acted on by an average force of this many newtons for that many seconds. Okay. Number 40. What is the magnitude of the change in momentum? Change we represent as delta and momentum is p. What is the change in momentum? You could either relate it, if you look at the reference table, as impulse j. You could also relate impulse as force times time. Or if you want to expand change in momentum, it's m delta v. The first three are on the reference table. This isn't, but you could easily understand that when you change momentum, you're specifically most likely changing the velocity instead of the mass in most cases. All right. Now, we are solving for change in momentum. They happen to give us the time and the force. So 0.01 seconds for time and 8,000 newtons for the force. Okay, so change in momentum, Ft equals 8,000 times 0.1, and that's 800 kilograms meters per second. And that is choice 2. Now, number 41, what is the magnitude of the average net force acting on the cannon? Okay, now be careful. So I'm going to draw this out. So we have the cannonball going this way, and then we have the cannon going the other way. All right, this is what happens in an explosion sort of scenario. Now we're looking for what is the force now on the cannon, since they gave us the force on the cannonball. Well, Newton's third law states that every interaction force has an equal but opposite reaction. Okay, so what does that mean? Even though these two objects have different masses, the force they experience is the same, equal in magnitude, just opposite in direction, which will then, because of their different masses, will affect their accelerations and their velocities after the explosion. As you can see, the cannon is bigger in mass, so it's going to have a smaller acceleration and a smaller velocity. And the cannonball, having a smaller mass, will experience the greatest acceleration after the explosion and result in a much faster velocity in the other direction. Okay, so it's the same force between these two objects, and that will be choice 3. Same force between them. Alright, number 42, here we have two objects, sphere X and sphere Y. Okay. This is -6 microcoulombs. This one's +2 microcoulombs. When they come together, charges are going to be exchanged to reach equilibrium, and then when they separate, they're going to settle into about the same charge. That's what equilibrium is. So when they come together, they pull their charges together. The charges will go back and forth until they reach equilibrium. And so this is my strategy to figuring it out. You're going to bring them together. And so -6 and +2, that's a -4 microcoulombs. I'm using micro because it's to the -6 power 10. And when they separate, they even out. And so this is now -2, and this is also -2. What is their net charge afterwards? That is choice 2 of -2 times 10 to the -6 coulombs. All right. Number 43. A constant eastward horizontal force of 70 newtons is applied to a 20 kilogram crate moving toward the east on a level floor. So the force here is 70 newtons. If the frictional force on the crate has a magnitude of 10 newtons in the opposite direction, what is the magnitude of the crate's acceleration? Okay, so here we have two forces, opposing sides. They're not the same. So you're going to have a net force value. They're not balanced. So 70 minus 10, because they're in opposite directions, you take the difference, and that's 60 newtons for its net force, sorry. Then you're going to plug this into F net equals ma. Newton's second law. 60 newtons is your net force. your mass of 20 kilograms, and you solve for acceleration, and that is 3 meters per second squared. Choice 3. Okay. Number 44. Which graph represents the relationship between the energy of photons and the wavelength of photons in a vacuum? Okay, so energy of photons, there are two equations for this. E equals hf, this is the modern physics section, and E equals hc over lambda, which is wavelength. Wavelength is lambda, so we're going to use this bottom one. Now, because wavelength is in the denominator, they have an inverse relationship, which means as energy increases, wavelength decreases, or actually wavelength should go first. As you increase wavelength, energy decreases. And the only one that fits the bill is choice 4. It's an inverse relationship. Because ultimately, the energy comes from the frequency. Frequency doesn't change depending on the medium. Okay? So higher frequency of those EM waves means higher energy. And because frequency already has that inverse relationship to wavelength, it's also going to, energy and wavelength are also going to be inversely related. All right. Now, number 45. Okay, 45 and 46 are related to each other. Here we have a standing wave being created by a student with a spring. What is the phase difference between the incident wave and the reflected wave at point P? So the incident wave, there's a lot of vocab here, is the one that goes first, the incoming wave into the wall. That's your incident wave. The reflected wave comes off the wall, okay? So your incident wave goes into the wall, and it gets reflected off the wall. So notice how it's completely inverted. So it kind of might have to tie into a little bit of your trig knowledge, but it doesn't have to with phase difference. And so it's kind of like how much are they corresponding? And we usually use 0 degrees and 360 degrees as completely in phase. All right. Because these mean they completely overlap perfectly. So 0 degrees and 360 degrees and any multiple of that relates to in phase completely. And then 180 degrees is halfway through, so that's completely out of phase. It's like complete opposites, and that's what we can see visually in this type of standing wave. Number 46. What is the total number of antinodes on the standing wave in the diagram? Alright, antinodes are the ones that go up and down, and so we count the number of bumps. That's 1, 2, and 3. There are 3 antinodes. Nodes are the ones that go on the ends of it, that don't move. 1, 2, 3, 4. There are 4 nodes, and 3 bumps for 3 antinodes. Okay, so since it's asking about antinodes, it's just choice 3. Number 47 is asking about the relationship of different types of wires based on cross-sectional areas and lengths. Here we have 4 pieces of the same material, copper wire, different areas and different lengths. We're looking for the one with the greatest resistance. Resistance in the wire is given by this equation. Resistivity, length, and area. Area has an inverse relationship with resistance. So we want a smaller area. Ideally, if we want resistance to go up, we want that smaller area. Okay, so we want that. And length is directly related, so we want longer length. Okay. So we want smaller area, so we got to pick one with A. And we got a longer area. Longer length. So it's not 1, it's going to be wire 2. Choice 2. Okay, moving on. And finally, the last 3 multiple choice questions of this test. Alright, number 48, the number of excess elementary charges on sphere A. So it has a charge of this. To have excess charge means you're either positive or negative. To be neutral means you have no excess. That means you have equal amount. So we're going off the charge itself, the charge of A. So it's positive 4 times 10 to the times 10 to the negative 6 coulombs. And we need to convert that to number of charges, number of particles, because each of them carries a specific amount. So 1e equals this, 1.6 times 10 to the negative 19. We're going to use some ratio. And the best way I tell you guys to convert between elementary charges and coulombs is this phrase, method. Okay? We are going from coulombs to elementary charge. So looking at our phrase, you multiply to go from elementary charges to coulombs. To go from coulombs to elementary charges, you divide. And it's all by this number right here. So, because we are going from coulombs to elementary charge, we're going to divide. Alright, so we're going to do 4 times 10 to the negative 6 divided by 1.6 times 10 to the negative 19, and that'll equal 5 times 10 to the 13th elementary charges. You should get a positive exponent because you can't have fraction of a particle. You need to have positive exponents to get a whole number multiples of these particles. Okay, number 49. What is the magnitude of the electric force between the two spheres? So now we're going to actually calculate the electrostatic force between them. And that's through Fe equals kq1 q2 over r squared. K is a constant. It's on the front of the reference table. I'm not going to fit all these guys. I'm going to use the E notation even. I'm not even going to put their units. 4e negative 6 times 3e negative 6. E is times 10 to the whatever exponent power is given afterwards. Keep in mind this is all in the numerator. I can't fit it all. R squared is the distance between them. So it's 2, and that's squared. Plug and chug into the calculator. And you should get close to 2.7 times 10 to the negative 2 newtons as your answer. Alright, number 50 is talking about Doppler effect. Here we have a moving sound source moving to the right. So notice as the sound source is moving, it's compressing the waves it's moving towards. So as it's moving, it's creating sound waves, but it's also pushing on those sound waves, making them shorter. So here the wavelength is shorter, but the frequency is higher. On the other end, you have longer wavelengths, but shorter frequencies, less frequent. The wave observed at point B, so we're describing point B. So it's higher frequency and shorter wavelength, and that's Doppler effect, as you can see from the diagram as well. And that's it. Now we're going to finally move on to the free response in part B2 and part C.